really has to do with ergonomically how it fits into their life.
Mhm.
Even if you can just offer the same level of control as what they would have with an eye tracker or with a mouse stick, but you don't need to have that thing in your face. You don't need to be positioned a certain way. You don't need your caretaker to be around to set it up for you. You can activate it when you want, how you want, wherever you want. That level of independence is so game changing for people. It means that they can text a friend at night privately without their mom needing to be in the loop.
Mhm.
It means that they can like open up, and browse the internet at 2 a.m. when nobody's around to set their iPad up for them. This is like a profoundly game changing thing for folks in that situation. And this is even before we start talking about folks that may not be able to communicate at all or ask for help when they want to. This can be potentially the only link that they have to the outside world. And that one doesn't, I think, need explanation of why that's so impactful.
You mentioned neural decoder. How much machine learning is in the decoder? How much magic? How much science? How much art? How difficult is it to come up with a decoder that figures out what these sequence of spikes mean?
Yeah, good question. There's a couple different ways to answer this. So maybe I'll zoom out briefly first, and then I'll go down one of the rabbit holes. So the zoomed out view is that building the decoder is really the process of building the data set plus compiling it into the weights. And each of those steps is important. The direction, I think, of further improvement is primarily going to be in the data set side of how do you construct the optimal labels for the model. But there's an entirely separate challenge of then how do you compile it into the best model. And so I'll go briefly down the second rabbit hole. One of the main challenges with designing the optimal model for BCI is that offline metrics don't necessarily correspond to online metrics.
Mm-hmm.
It's fundamentally a control problem. The user is trying to control something on the screen, and the exact sort of user experience of how you output the intention impacts their ability to control. So, for example, if you just look at validation loss as predicted by your model, there can be multiple ways to achieve the same validation loss. Not all of them are equally controllable by the end user. And so it might be as simple as saying, oh, you could just add auxiliary loss terms that like help you capture the thing that actually matters. But this is a very complex, nuanced process. So how you turn the labels into the model is more of a nuanced process than just like a standard supervised learning problem. One very fascinating anecdote here, we've tried many different sort of neural network architectures that translate brain data to velocity outputs, for example. And one example that's stuck in my brain from a couple of years ago now is at one point we were using just fully connected networks to decode the brain activity. We tried an A/B test where we were measuring the relative performance in online control sessions of sort of 1D convolution over the input signal. So if you imagine per channel, you have a sliding window that's producing some convolve feature for each of those input sequences for every single channel simultaneously. You can actually get better validation metrics, meaning you're fitting the data better and it's generalizing better in offline data if you use this convolutional architecture. You're reducing parameters. It's sort of a standard procedure when you're dealing with time series data. Now, it turns out that when using that model online, the controllability was worse, was far worse, even though the offline metrics were better.